Greetings again. I'm Peter Denning. We're working our way in through the Harnessing AI class. This is our third session. Today we're going to be talking about the next stage of machines in our hierarchy of learning machines. And today we're going to be talking about what is called the rule-based AI. So remember, yesterday Professor Cole was talking about automation in general, and now we're going to bring automation into what we can do with computing machines. One thing that we know computing machines are good at, not the only thing we know they're good at, one thing we know they're good at is following the rules. So if we say, here are the rules, machine can follow the rules. And there's a lot of things that we say that when we learn them, we start by learning what the rules are, and then we follow the rules. So for example, if you were learning chess or checkers, you'd want to know what's the rules of the game, and then you'd follow the rules as you play the game. And if we could understand the rules, we could put the rules into the computer, and then the computer can do that job. We don't have to know all the rules ourselves. So as this idea of capturing our knowledge in the form of rules was one of the earliest ideas in trying to move in the direction of machines that learn. In 1952, there was a man named Arthur Samuels at IBM who created a machine that would play chess. And he wrote down all the rules of chess and rules for different types of chess situations, and programmed them into the machine. The machine played chess pretty well, and he had a feedback mechanism in there so that it would improve the rules as it went on. And so this thing became pretty good at playing chess. It wasn't chess, did I say check? It's checkers. It was easier than chess. That inspired other people to go after the game of chess, and it actually, chess programs got better and better over the years, and finally, I think it was in 1997, a IBM chess machine called Blue Machine beat the world champion Garry Kasparov in chess games. So the machine had finally, after 30 years of evolution, got to the place where it could beat the world grandmaster at chess. So that gave a lot of people a lot of confidence that this approach would be a good way to build machines. One of the culminations of that was called the expert system, which was a software system that would, by acquiring enough rules and enough facts about the world, would be able to behave like a human expert. And we have some expert systems that have done quite well in that regard. So today we have Professor Vinnie Monaco here to talk about all this with you. And he's going to talk about where all this comes from, what it's capable of doing, and maybe some of the limitations of it. It's a very interesting class of machines that we have. So Vinnie, I think you've been here about 3 years now, is that right? So
yeah, just about 3 years.
He's already an old hand at NPS, and he's been doing very well. He previously worked for the Army before he came here, and has had a lot of prior experience with machine learning. So I introduce Professor Monaco. Over to you.
I appreciate it. Thanks for the introduction, Peter. And today I'm going to talk about rule-based AI. Just to jump right into it, I'll start with a background, which I'll go over some of the general programming techniques that you need to implement a rule-based AI. Talk about some early attempts which viewed expertise as logical reasoning. And then I'll spend some time talking about expert systems, which were based on the hypothesis that you could attain intelligence in a machine at a particular task, kind of emulating an expert, and finally conclude. So Rules are essentially just if statements. They're implications, and these can establish a pre and post condition. So we could say if it's a federal holiday, then there's no class. So that's a rule. You can also use a rule to encode a property or a relationship. You could say all baseballs are rounds. As a rule, this would be interpreted as if X is a baseball, then X is round. You can also use rules to specify a sequence of actions that you might need to take in order to do something. So in order to request leave, you have to submit a form. Rules are basically just implications. And using the rules, a rule-based system performs inference. So starting with a bunch of rules and facts, we'll perform inference over those rules and facts to try to get at some conclusion. There's really two different ways that inference is performed in rule-based systems. The first is working backwards, called backward chaining. So in this case, we're going to start from our conclusion and then work back to our knowledge base, which is basically just contains the rules and the facts. So we'll start with our conclusion, a baseball can roll away, and just trying to determine, is that true? Can we prove a baseball can roll away from our knowledge base, which might contain if something is round, then it can roll away and the baseball is round. So that's backward chaining. The other way in which we could perform inference is forward chaining. So we start with our knowledge base, start with, say, this rule and this fact. If something's round, then it can roll away, and baseball is round. And what can we derive from that? Can we reach this conclusion, or maybe there's some other conclusions that we might be able to derive from that knowledge base? So these are the two main ways in which inference is performed in a rule-based system. So what actually makes up a rule-based AI, besides the facts and the rules, these comprise what's called the knowledge base, and then the inference engine. We typically have a working memory, which is kind of just like a scratch pad, a place where we can remember things or write things down and recall them later on, and some interface to interact with the system, a way to ask it questions or get back answers. A way to query the rule-based AI. A couple of the oldest high-level programming languages still in existence and still somewhat widely used today were developed around this idea of building a rule-based AI. So Lisp, which I won't spend too much time talking about today, was developed by John McCarthy. It's one of the oldest, if not the oldest, high-level programming language still somewhat widely used. And Prolog, which I'll talk a little bit about, is one of the others, which is a logic-based language. So if we want to take the preceding example and actually do inference, actually try to get it to do something interesting and give us back some results, we could do this in Prolog by formalizing that rule and that fact, and that would look just like this. We would take our rule and say if X has a shape that's round, then X can roll away, and a fact that just says a baseball is round. And then Prolog is a backward chaining system, so we would then come up with some query. We want to ask it, well, can a baseball roll away? So this kind of strange syntax here, the question mark dash, is just denotes that this is a query. We're asking, is this true? Can we prove a baseball can roll away? And through backward chaining, Prolog, which has a built-in inference engine, would say, yes, this is true. We can prove that statement, and would return an answer of true. So a lot of the early attempts at rule-based AI revolved around this idea of trying to build a system that was rule-based, that manipulates symbols. So I'll take a couple minutes to just look at some of the early attempts. One that Professor Denning already mentioned, which was developed by Arthur Samuel, which was a system to play checkers, which worked. It was based on what's called alpha-beta pruning, which is an algorithm to just search through all the game states that you might be able to reach in checkers and do that pretty efficiently, so you can figure out the next best move to make. And actually, alpha beta pruning, this technique was the best way in which you could play checkers and chess for a pretty long time. It's actually, if you place some constraints on the amount of compute power that you're allowed, that your compute engine is afforded, then alpha beta pruning is actually probably still one of the best techniques with compute constraints, could even perform better than a neural network. So the leading chess engines were based largely on alpha beta pruning for decades. Following this, in the same year, a general problem solver, which was developed by Simon, Shaw, and Newell. This was supposed to be a kind of universal problem solver, but in reality it could only kind of deal with toy tasks or toy problems like the Towers of Hanoi. So how do you move all the rings from one side to the other, given certain constraints in the way you're allowed to move the rings around. A couple years later, Saint, Symbolic Automatic Integrator. This was developed at MIT and written in Lisp. So this was a system that could solve problems on a freshman calculus exam, solve integration problems, and it did fairly well. It could solve all. They demonstrated it could solve all but 2 problems on in a freshman calculus exam taken at MIT. A year later, a system called Analogy, which was based on coming up with analogies, building rules through analogical reasoning. So A is to B as C is to what. So this was aimed to kind of solve these IQ test style questions, such as shape A is to shape B as shape C is to something else. And there's another system in the 60s called Student, which could solve, developed by Daniel Bobrow, which could solve word algebra problems. So a lot of these early attempts at building rule-based systems led to a lot of optimism in what's called good old-fashioned AI. So the AI built around manipulating symbols and constructed rules and facts and symbol processing. This optimism is codified in a couple quotes. Turing predicted that by the turn of the century, we would have machines that could converse just as well as a person. Minsky, some would agree with that, saying that within a generation, the problem of creating artificial intelligence will be substantially solved. And a couple years later, he actually doubled down and said in 3 to 8 years, we'll have a machine with the general intelligence of an average human being. Well, of course, none of this happened, and we'll take a look at why that is shortly. But one catalyst, or what's thought to be a catalyst for what is termed the first AI winter for this optimism kind of coming to an end. One of the triggers for this was a book published by Minsky and Papert in 1969, which demonstrated a lot of the shortcomings of actually the perceptron, which is a kind of neural network, and led to interest kind of the sentiment in the field shifting and interest shifting to other areas. So this book was thought to be somewhat of a catalyst, but there were a lot of other factors involved in what led to the first AI winter. I think it's worth looking at some of these, since we're surrounded by a lot of hype and optimism today. So one was looking at the early attempts. These were focused on solving toy problems, but when you try to transfer them to the real world, you experience a combinatorial explosion in just the space that you have to deal with and search. So even considering a game like checkers or chess, which itself has a huge state space, think about all the possible valid game positions in a game of chess. When you move to the real world, tasks that require reasoning about physical objects, the space is even larger than that, and noisier. A combinatorial explosion of real-world problems combined with a lot of overpromising by some of these early attempts. There was also it was followed by and perhaps influenced. There's a Mansfield Amendment. So this was an amendment that in the U.S. that said that the military could no longer fund basic research, had to fund research that supported military operations in some way. And DARPA was disappointed with a speech system developed at CMU, which again was rule-based and kind of suffered from the same kind of problems. It was very rigid, and when you try to apply these rule-based systems in the real world, that rigidity has trouble dealing with the noise that you have in the real world. And finally, the kind of pinnacle of all this pessimism was the Lighthill report. So this was a report which came out in the UK, which basically summarized the shortcomings of AI at the time, and this is thought to have led to a lot of revocation of funding for basic research in AI. Following the first AI winter, the sentiment shifted a little bit, and folks didn't quite give up on rule-based systems. They thought, well, we can't build a general rule-based system that can achieve general intelligence, but maybe if we pick one specific problem, pick one thing, and become an expert at that one thing. So try to do one thing very well. So this is based on the hypothesis that a rule-based logic system could reach human expert levels on one very specific problem. So this gave rise to expert systems, which expert systems are rule-based systems developed to become, with the aim of becoming an expert at one specific problem. What this typically involved was a knowledge engineer, so someone that actually tried to formalize all the things that you need to know to solve one specific problem. For example, Dendril was a system developed by Edward Feigenbaum, which aimed to identify unknown organic molecules using knowledge of chemistry. So what the system comprised of was as much of the expert knowledge in chemistry as could be formalized into a knowledge base, which involved it was called a knowledge engineer working with some domain expert, working with an organic chemist, and trying to extract all the things that organic chemist knows and put it into a knowledge base, formalize it. So remember, all that knowledge, those rules have to be formalized in order for the rule-based system to work. There was another well-known system called Mycin, which identified bacteria causing severe infections. It was never used in practice, although it was of fairly wide interest. And another system which was actually quite commercially successful called XCON, which was developed for the Digital Equipment Corporation. This was a system that selected computer components based on customer requirements, and the DEC estimated that it saved them about $25 million a year. So expert systems in the starting in the 80s started to become prevalent, and at some problems they did do quite well. It was also thought at the time that what we needed was more compute power, that in order to achieve intelligence with a rule-based system, we needed massive parallelism. We just need to throw more compute at it. So this was the one of the main ideas behind Japan's 5th generation computer project, which the 5th generation come from this this moving from vacuum tubes to transistors to integrated circuits to microprocessors. So those were the first 4 generations. And the next step, the 5th generation, was scaling out laterally, building these systems in with massive parallelism. So the idea here was to use massive parallelism to do logical inference. So we don't just need to do logical inference, just do it faster and do more of it, and then we can achieve intelligence. So this project started in the early 80s and lasted 10 years. It was about $500 million. It ultimately ended, and some argue whether it was a failure or ahead of its time, since the some of the ideas in the 5th generation project did live on to later research, did find their ways evolve into other fields, but the project ultimately ended and is considered by some as a failure. Of course, at the same time, the U.S. also launched its strategic computing initiative, which wasn't tied directly to AI, but more generally to scientific computing. And this project was thought largely to be a success compared to the 5th generation project. So in the late 80s and early 90s, we started to experience the second AI winter, which was due to partly commercialization of expert systems slowing down. The machines developed specifically for inference, so so-called Lisp machines, didn't perform quite as well as the manufacturers thought they would. And the 5th generation project ending was also a catalyst for the second AI winter. But largely, I mean, looking at, in hindsight, some of the reasons why expert systems kind of failed to give us AI. One, we can look at some of the limitations of expert systems. One, they don't learn easily. I'd say easily because in most of the expert systems that were developed, when you get new information from the world, or the rules change, or something changes that doesn't, it makes your knowledge base stale, no longer reflects what's actually true. That typically required a manual process. So there was this bottleneck of the knowledge engineer having to take the information, those rules that we might have and know and remember in natural language, and then formalize that into the knowledge base. So there's this bottleneck in there, which besides making them not be able to learn easily, made them expensive to maintain, and they were somewhat restricted by the size of the knowledge base. So this, the idea at the time was that they lack a lot of the common sense or background knowledge, which I'll talk more about. And that actually is one of the main limitations, which I'll spend some time on the next slide, is that they lack an understanding of what human expertise really is, and lack common sense. And it's not possible to explicitly define some rules. So I'll show an example of that shortly. So first, going back to that second to last point, that the last point, that's not possible to explicitly define some rules. Look at an example that's difficult for a rule-based AI. So if we take an example image and we just want to say recognize sunglasses in this image, well, how do you write a rule that encodes that? If I have all this stuff in the image, then I have sunglasses. Then I can say there's sunglasses in this image. It's not practical. It's not possible to do this in a general way. I mean, to come up with a rule an implication that says, well, if I have all this pixel is pink, and the pixel around next to that is black, and so on. It's not really practical to come up with a general rule in this way that does this kind of low-level perception. And this highlights one of the dichotomies between the capabilities of rule-based systems and the things that humans are good at, which include these low-level perceptual tasks, looking at something and recognizing what it is, compared to these rule-based systems, which are very good at manipulating symbols, performing arithmetic using large numbers and logical inference and so on. This dichotomy is referred to as Moravec's paradox, and reflects kind of the differences in what machines are good at and what humans are good at. So that's one of the main limitations of rule-based systems, is just some of these low-level perceptual tasks are difficult to, if not impossible, to encode in a rule-based system. The other is what's called the context problem, or this lack of understanding of what human expertise really is. So this, I think, is exemplified with what's called the Winograd Schema Challenge. If we take an example here, we have two sentences where they differ by only a single word there at the end of the sentence. The goal here, the goal of the Winograd Schema Challenge, is to determine what they refers to. So if we look at they at the end, what does they refer to? Does they refer to councilmen or demonstrators? Well, in the first example, based on the word feared and all of the background knowledge that we have through experience, we can determine that the antecedent of this ambiguous pronoun, they, refers to councilmen. So they feared violence, meaning the councilmen feared violence. And the second example, though, where we replace feared with advocated, we would now tie to demonstrators instead of councilmen. So just based on changing that one word affects where we're going to attach that pronoun they to in that sentence, which, to a machine without that background knowledge is going to be ambiguous. So that's one of the main limitations of these systems based on rules, is there's so much of that background knowledge, that common sense, and it's probably not practical to try to encode, to formalize all of that into a knowledge base. Despite that, someone has been trying to do exactly that for about 2 or 3 decades. So Doug Lennart started a project called Psych in the 80s as an attempt to try to solve this common sense problem. Just take all of that common sense that we have and kind of take for granted and try to formalize it and put it into a knowledge base. And if we do that, then we can achieve some level of intelligence. So that's a massive undertaking, to say the least. Requires formalizing facts and rules that you don't really think about, that you might learn at a very early age. If I take an object and drop it, it's going to fall to the ground. Things like that, this common sense knowledge that would enable reasoning and enable us to solve some of these problems where we have an ambiguous pronoun, or the context is going to help us reason or perform inference. So it's still going. Psych just recently started to commercialize, but never really lived up to its expectations, at least not so far. So I want to look at this point some of the differences between a rule-based system and a neural network, although you haven't seen neural networks in this course yet. Just to give you an idea of what's to come. So if we want to represent an apple, the concept of an apple in a rule-based system. The apple would be represented, one way to represent the apple is as a tree, using all these symbols that encode its shape and its color and its dimensions and so on. So in a rule-based system, we work with symbols. In a neural network, however, the alternative representation of an apple would be through vectors, through what are called the subsymbolic representation, which is also referred to as a connectionist approach. Now, these two approaches are fundamentally different, and we know that that humans, our only example of real intelligence can do both of these simultaneously in a system that is perhaps connectionist, that's working with these subsymbolic representations. So one of the main outstanding problems in both in neuroscience and AI is how do you integrate these two approaches, this subsymbolic representation and subsymbolic way of processing with symbolic processing. So how do you achieve both of those things in the same system is really an open question. So despite all the limitations of rule-based systems, there are some advantages. One being that they're computationally inexpensive. So it's generally quick to perform inference and arithmetic to manipulate symbols on a digital computer. The results that you get are explainable. We can trace back exactly why or prove why we got a result that we did, which means they're well suited kind of by definition for symbol processing. Well, if we look at the direction some recent work on neural networks is going in, some of this work is actually using ideas and drawing from ideas that are decades old, trying to integrate some of these symbol processing approaches into neural networks. So some groups believe that just a plain old neural network is not sufficient. We need to imbue with symbol processing capabilities, with the structures and mechanisms to process symbols. So the differential neural computer was is one of the recent developments, or I suppose not so recent now, but has led to a number of recent developments where neural networks are being augmented with memory and the ability to process symbols, actually drawing from some of these ideas that date back to the 80s that we're looking at how do you process symbols, how do you converge these two approaches, symbolic and subsymbolic symbol processing. So if you're interested more in the history of some of the good old-fashioned AI and limitations of AI in general, I'd like to point out these two sources. One is a paper which is actually, I believe, a book chapter by Melanie Mitchell. The other is a book. Both these would be worth a read if you're interested in looking at some of the limitations and why AI is so difficult, why it's a hard problem. That concludes my talk. I'd be happy to take questions now.